Imagine a future where Earth's energy needs are met by an ancient, hidden source, a crack in the ground that holds the key to an endless supply of power. This isn't science fiction. It's a real possibility that scientists are exploring right now. The Midcontinent Rift, an ancient geological feature, has captured the attention of researchers for its potential to unlock a natural and sustainable energy source. This rift, formed over 1 billion years ago, is a treasure trove of magma, water, metals, and even natural hydrogen. Picture it as a hidden reservoir, waiting to be discovered and utilized. For decades, scientists have been intrigued by the rift's potential for hydrothermal energy, but now, their focus has shifted back to the magmatic deposits within. Copper-nickel sulfides and nickel deposits have been explored, hinting at the rift's untapped energy potential. But here's where it gets controversial. Can the iron-bearing rocks within the rift, when interacting with underground water, produce usable hydrogen gas? On paper, it sounds like a dream, but the real challenge lies in the field, where chemistry, geology, and engineering must come together to provide answers. Natural hydrogen, often referred to as white hydrogen, is a fascinating category. Unlike its green counterpart, which requires significant power and facilities to split water, natural hydrogen forms when water reacts with specific minerals beneath the surface. Earth provides the perfect setting and ingredients for this reaction, and no additional facilities are needed. This process is unique. It's not a fixed deposit that depletes over time. As long as the right conditions are met, water, reactive minerals, heat, and open pathways, the reaction can continue, renewing the resource as it cycles. The rift's geology is a complex tapestry. Thick stacks of mafic rock, rich in iron and magnesium, drive water rock reactions that release hydrogen. The rifting process has also created fractures and faults, some storing fluids and others allowing movement. Over time, pulses of heat and mineralizing fluids have created a complex network, setting up ideal conditions for hydrogen formation, migration, and collection. Porous layers, often sealed by tighter rocks above, provide ideal conditions for gas accumulation. The rift's varied geology offers numerous such pairs at various depths, creating a diverse and promising landscape for exploration. A research group in Nebraska has taken up the challenge to test whether measurable amounts of hydrogen are formed where rift rocks are accessible to modern drilling techniques. They want to understand if the gas accumulates in traps or escapes through leaks, and whether microbes consume it before it can be harnessed. The team has drilled a test well into the rift rocks at a depth of several thousand feet, a sweet spot for exploration. It's deep enough for natural trapping and isolated from shallow groundwater, yet shallow enough for practical drilling and monitoring. They analyze gas compositions, study hydrogen's movement through fractures and pores, and investigate whether it dissolves into salty formation water or adheres to mineral surfaces. If it dissolves or absorbs too easily, capture becomes a challenge. If it moves too freely, it may escape before it can be collected. Deep within the rock, microbial life thrives without sunlight, surviving on chemical energy. Some of these microbes even eat hydrogen. The researchers study these organisms and measure their hydrogen consumption rates at the depths where they reside. If the microbial community is thriving, it could consume hydrogen as fast as it's produced. But if chemistry or heat limits their activity, more hydrogen could remain available. So far, the data is encouraging. Scientists at the University of Nebraska-Lincoln believe that the geomechanical and biogeochemical conditions within the rift may limit the loss and consumption of this naturally generated hydrogen. This means that trapped hydrogen could exist at economically significant levels in the mid-continent subsurface. It's deep enough to be stored but shallow enough that we can access it, said Carrie Weber, a professor at UNL. The geology is in our favor. The process of hydrogen generation within the rift is fascinating. Iron-rich minerals like olivine and pyroxene can react with water, splitting water molecules and releasing hydrogen. Fresh mineral surfaces react quickly, so fractures exposing new rock are crucial. Temperature controls reaction speed, and pressure influences how much hydrogen dissolves into brines or rises as a gas. Other natural processes within the rift also contribute to hydrogen production. Radiolysis, The breakup of water molecules by natural radiation in rock can generate hydrogen. The interaction of ultramafic rocks with water, known as serpentinization, is another contributor. The rift's mafic and related rocks offer multiple pathways to hydrogen, with local conditions determining which process dominates. Hydrogen's importance as an energy source cannot be overstated. In fuel cells, it produces electricity and water, and in high-temperature applications, it can replace fossil fuels, reducing carbon dioxide emissions. Heavy trucks, some industrial furnaces, and backup power systems are already moving in this direction. If natural hydrogen can be harnessed on a large scale and at a reasonable cost, it could complement manufactured supplies and reduce the need for new facilities and the electricity they require. If the rift systems continue to generate hydrogen over time, production could be steady enough to serve as a baseload, providing a constant, limitless supply. To make this plan a reality, several factors must be present. Measurable hydrogen at depth, stable concentrations over time, and evidence of trapping beneath reliable seals. Wells must sustain flow without rapid decline, and surface equipment must efficiently separate hydrogen from other gases. Proven monitoring methods must track and confirm the system's integrity year after year. Meeting these requirements would indicate a resource capable of supporting fuel cells, turbines, and process heat without sacrificing long-term sustainability for short-term gains. The current work aims to test whether these conditions exist, creating a practical resource that wells can safely access and manage. It's a collaboration between chemistry, geology, microbiology, and engineering, all working towards clear answers. Whether the outcome is production or a map of areas to avoid drilling, the result will enhance our understanding of clean energy options shaped by Earth's own chemistry. The full study has been published in the journal or Geology Direct, offering a deeper dive into this exciting research.